Let's look at another way we can represent and solve these kind of problems. You can use a tree diagram. Now, everybody's brain works differently, right? And we did talk a little bit about trees on the Monday last week, and that's something, if you've taken 2420, you should be familiar with trees, and there's more about them in chapter 11 in the book, but we're just going to use it at the very, very base level. Some people, the trees make more sense. Some people, the counting ways we've been doing it makes more sense. They're both good ways, but here's the basic idea. You make a tree and you branch for every possible outcome of what you're looking at, right? Every possible choice. And then when you complete the tree, you count up the number of leaves, and that's the answer of how many possible outcomes there are. So what's a leaf on a tree? You guys remember? Yeah, it's a node on a tree that doesn't have any children, right? It's not a parent. It's a childless parent, I guess. I guess you can't be both, right? But no children, right? Okay. So if you count up all the leaves, then that will be your answer. So let's look at how this might play out. This is our question we talked about a minute ago. How many nibbles can exist with no consecutive ones? So that's a 4-bit string, right? And it can be any combination of ones and zeros as long as there's no 2 ones in a row. Now here's how we do this. Remember there's 4 levels here, right? There's choosing the first bit, choosing the second bit, the third bit, and the fourth bit. So we start off with our root here, which is just sort of nothing, and we can branch 2 ways, right? I can choose a 1 or a 0, right? So we choose a 1 or a 0. Oh, that shouldn't be there. That's 0, 0, 0. That's fine, I'll leave it in. That should have been deleted. It'll probably go away in the next slide. Okay, so we can branch to a 1 or a 0, right? Now, for the second bit, what are our options? What's our option for the left bit there, the 1? It's only a 0, right? Because the rule is we can't have 2 ones in a row, right? Yeah, the one, so the left, so we're looking at this guy right here. What are its choices for the second bit? If that's the first bit, the second bit cannot be a 1, right? Because that goes against our rule. All right, so that's going to be just a 1. What about this? It could be a 0 or a 1, right? Okay, good. So it looks like that. I told you that 0, 0, 0 would go away, right? So it looks like that. Does that make sense? Now, looking again, what are our options? What's our options over here for the third bit or bits, and for this and for this? What are our options for each of those?
1, 0, 0, 0.
Right, so this first one here, it can be a 1 or a 0, agreed? This one can only be a 0, because otherwise it'd be 2 ones in a row, and this one could be 1 or a 0. Make sense? Okay. So hopefully my map is accurately reflecting that, and it does. Okay, so now that's the third bit. Now let's pause for a minute, make sure we understand what's going on here. Right now I'm saying if we were doing 3-bit strings, then we're done, right? And the 3-bit strings that could exist is a 1, 0, 1 or a 1, 0, 0, right? Or a 0, 1, 0 or a 0, 0, 0 or a 0, 0, 1. Those are all the possible things, which is a total of 1, 2, 3, 4, 5, right? We're going one more level though, and so based on what we've seen so far, what do we know about the first one there, the 1 on the far left? What's the next possible children?
0.
Just 0, right? Just 0. The next one there.
0, 1.
0, 1. Next one. 0, 1. Next one.
0.
Just 0. Last one. 0, 1. Right? That's the fourth bit. So now that's a total of 1, 2, 3, 4, 5, 6, 7, 8. Right? If we just count up the leaves right there, that's 8. There's 8 leaves if I counted right. Yeah. Okay. And what are the numbers? Well, it's these, right? It's 1, 0, 1, 0, which is following this path from here to here to here to here. And then it's 1, 0, 0, 1, which is here, 1, 0, 0, 0, and then so on and so forth. If you follow each path, you'll get those numbers. So that's a way to use tree diagrams. Okay? Make sense? I think that's out of the book. There's also another one in the book, which is this one right here. A playoff between 2 teams consists of at most 5 games, so no more than 5 games. The first team that wins 3 games wins the playoffs. All right? How many different ways can the playoffs occur? Can the playoff occur? So we're gonna have a tree that is how many levels deep? Yeah, it's gonna have 5 teams, right? Or 5 games. Game 1, game 2, game 3, game 4, game 5. At the most, all right? So I'm just gonna show you the diagram right out of the book because making a 30,000 slides to do this animated would have been a pain in the butt. So I just copied and pasted it right out of the book here. But let's talk through it, okay? This is what it looks like. We have this is the starting point, which is just our root node. And then we have game 1, which is right here. And in game 1, either team 2 will win or team 1 will win. Agreed? Right, that's kind of obvious. Now, game 2, we have this chunk of stuff right here. These are all the game 2 options. Well, in game 2, where team 2 won the first time, team 2 could win again or team 1 could win. Yeah? Over here, team 1, well, team 2 could win or team 1 can win, right? So now we have a path that goes 2-2 or 2-1 or 1-2 or 1-1, right? Make sense? Yeah? Good? Third batch here. Okay, this is the third possible result. Let me clear some of this out here. Let's just look at game 3 results here. Okay, now remember what I'm looking at here is playing after what happened in game 2. In the event that team 2 won on game 2 after also winning game 1, there are 2 outcomes. They could win a third time, which means they're done. They won the playoffs. They won 3 games. Or team 1 could win the next one, right? Or in the event that team 2 won the first time, team 1 won the second time, well, then it could go to team 2 or team 1 again, and so forth. Those are the different options, right? Everybody see that? Okay? Last, or not last, but the next one, game 4, you're starting to see that these leaves are appearing here because we're getting to these blue ones where there is a final, right? So in the event, let's go this path here. Team 2 won the first one, they won the second one, they lost the third one, but they won the fourth one. That's 3 games. They're done. That's your final root or your final leaf, and there's no more children, right? And if you follow this all the way through, eventually, by the time they get to the 5th game, there will always be a scenario where somebody won 3 times. But these are all the possible ways this could happen, right? It's like those movies where somebody can see the future and they see all the possible futures, right? Like Doctor Strange would be a perfect current example of that. How many did he see in Infinity War? Some 14 million. Do you remember the number? Nobody? You guys not seen Infinity War? You haven't? Okay, leave class right now and go watch that movie. What are you doing here, man? Oh, man. Yeah, anyway, sorry. That's where everybody's at. Okay, don't spoil it. If you haven't seen it, don't spoil anything. But now, count up the blue dots, right? Those are the leaf nodes, right? 1, 2, blah, blah, blah. I don't know what the number is going to be, but you can see what the total is by just counting those up, right? We feel okay about that? Make some sense? To the whiteboards. All right, looks like everybody got it correctly, and I love the little added detail with the shirt as a root node there. That's funny. So, and this is exactly what you guys did, right? We start off with the root node there. You put out all the sizes, and then you put all the children of each of those sizes, and then you count up the leaves. You count up the leaves, you'll get a total of 17, right? Questions about that? Pretty straightforward way to use it. Okay, we good? We're gonna change gears now. So the pigeonhole principle, let's talk about this. It's a pretty simple idea. There are at least 2 objects in one box when there are more objects than boxes, right? That's pretty straightforward, right? And we use the example of pigeons, right? These are pigeonholes. And so one pigeon flies in and he gets in one box. And then another pigeon majestically flies in and gets in another box. And then another pigeon flies in. And then a 4th one flies in. And then another one. Bet you don't know what's going to happen next. Another one flies in. No. Now there's 6 pigeons, 6 boxes, but number 7 flies in. He's like, hey, wait a minute. And he gets angry. And he looks at that pigeon and says, hey, scoot over. And the pigeon's like, are you threatening me? And he's like, yes, I am. Scoot over, man. So now there are two pigeons in one box, right? So again, the thing says there are at least two objects in one box when there are more objects than boxes. How many objects do we have? 7. How many boxes do we have? 6. So we have a collision, right? So there's more objects than boxes, therefore one of the boxes will have at least 2. Now, I could have put all of the pigeons in one box. It would still be true that I had at least 2 in one of the boxes, right? All right, that's the pigeonhole principle. This is very important, and I'm such a bummer that you missed that your instructor didn't show for the hash tables, because this principle comes into play there. It comes into play in a lot of places, and we'll look at some simple problems that are pigeonhole problems, but that's a very useful thing in discrete math and in programming in general, when you get to hash collisions and learning how to create a good hash code and making a hash table. So that's cool stuff. So here's some examples that are simple problems. How many people need to be in a room to guarantee that at least 2 of them have the same birthday? Oh, don't answer that just yet. That's one question. That's actually a pigeonhole problem question. How many students need to exist in a classroom to guarantee that you will find at least 2 students with the exact same number of points on a 100-point exam? Assuming that we're not using half points and everything, just using 0, 1, 2, 3, 4, 5, right? How many words are needed to guarantee that at least 2 of them start with the same letter of the alphabet? Those are all pigeonhole problems. They're also counting problems, right? And we want to count what the total number is. So any thoughts on any of these? Do we know the answer to any of those?
367.
So 367 for the birthday one. Why?
Leap year.
Say again?
Number of days in the year plus leap years.
Plus, right. So there are 365 days in a year normally, but if you count a leap year that has the February 29th, that year has 366. There are 366 possible birthdays. That's it. Everybody's born on one of those 366 days, right? To guarantee that somebody else has that exact same birthday, you need a 367th person. No matter when that person was born, it'll match somebody else. Now, that's like a worst case scenario, right? It could be that all 366 people or 367 were born on the same day, right? Could be. That's when all the pigeons are in one cubby. That's okay. What are the pigeons? What are the holes? Okay? The holes are the birthdays and the birth dates possible, and the pigeons are the people that have the birthdays, right? How about the next one? How many students? Why 102?
0.
Yeah, you could get 0, right? So there's 101 possible points. Last one, 27, because there are 26 letters of the alphabet. And that was my other smart aleck reply in case somebody said which language, right? Nobody said it. All right, yeah, so we got all the numbers correct. We understand why, right? There are 26 letters in the alphabet, and if I were to write down 26 words that all started with a different letter of the alphabet, the 27th word, no matter which way I slice it, it will start with the same letter as one of those other 26 words. Dig it? That's pigeonhole stuff, okay? All right, so here's the formula for this, the generalized formula for this. If there are n objects, so pigeons, if there are n pigeons, placed into k pigeonholes or boxes, then there is at least one box containing at least the ceiling of n divided by k, right? That's what the little bracket thing's there, the ceiling. You guys remember what ceiling means? Yeah, it just rounds it up no matter what, yeah. So 2.1 rounds up to 3, right? 2.00001 rounds up to 3, right? It just rounds it up, right? So let's take a look at that and see if that's true. In this scenario with our 7 pigeons, n is 7, k is 6. Well, what's 7 divided by 6? It's 1 point something, right? We ceiling that and we get 2. And we see there's no way to arrange those cubbies and pigeons such that there's no cubby with at least 2. It's impossible, okay? And again, this is simple stuff, right? But understanding the way it works and how it applies to our field is important. So let's take a look at this example problem here. Among any set of 21 decimal digits, there must be 3 that are the same. You understand what that's saying? If I had 21 decimal digits with 21 single-digit numbers, right? At least three of them will be the same digit. Yep, makes sense? So let me just throw out some random numbers here. Those are just random, I literally on my keyboard, I just typed random numbers, right? Just to see what I would get. And look in there and you'll see that there's more than 3 ones, right? You'll see that there's more than 3 zeros. There's at least 3 eights I can see, right? But that's a random string. Let's try to orchestrate it to the worst case scenario. I'm gonna write out 10 digits, 1 through 0, or 0 through 9, however you wanna look at it. And then I'm gonna do 10 more, so that's a total of 20 digits, right? No matter what the third digit is, it's gonna be a triplicate of one of those, right? No matter how you slice it, right? And this is me orchestrating a worst case scenario. If I did not do a worst case scenario, we're gonna have something that's 4 of the same digit, or 5 of, or whatever, right? Does that make sense? Conceptually, that's a pigeonhole problem, okay? What are the pigeons and what are the holes in this case?
The holes are the 21 possible digits.
Close. Those are the pigeons. The holes are the 10 slots, right? The 0 through 9. Those are the 10 possible places that you can put a pigeon. It can either be a 0 or a 1 or a 2 or 3, right? You have 10 boxes. And in box number 1, I'm gonna put all the zeros and so forth, right? So N is the number of objects, there's 21 objects, and K is the 10 number of boxes to place them in. I can only put them in, it can only fit in a 0 through 9 box, right? If all 21 digits happen to be a 1, they'd all be in one box, right? So these kind of problems, it's very important to be able to recognize what's the pigeon and what's the hole, right? Right? There's an old riddle that I heard when I was a kid that I didn't know it was a pigeonhole problem, but it actually is. And so I'm going to say the riddle, and then if you know it, don't shout it out. Just think about it for a minute. If you don't know it, see if you can figure it out. But if you do know it, don't blurt it out. So the basic idea is this. It's dark, and I wake up in the morning to get dressed, and I don't want to wake up my wife, so I don't want to turn on the light. And I only own blue socks and black socks. That's all I own. I got a drawer full of, 50 black socks and 50 blue socks, right? I want to just grab a handful of socks without look, because I can't see, it's dark, and guarantee that I have at least 2 that match. That's what I want to do. So don't answer it out loud, but what's the minimum number of socks that I would have to grab out of my drawer to guarantee that I had a matching pair? That's the question. Don't answer it just yet, but think about that for a minute. Just show of hands, who knows? Okay, good. Why don't you think about it? Have you seen it before? Or do you just figure it out right now? Don't answer it, but just.
I think I figured it out. I
Okay.
might have heard it wrong, so.
That's okay. So nobody's heard that one before. That's good. That's good. There's some days where people have never heard of things I talk about where it's a bummer. I'm like, man, I'm getting old. I don't know this stuff from the 80s, the 70s. Then other days where you don't know it, I'm glad because I want you to think about it. So anybody else think they got it figured out? Yeah, you got, don't say it, but you have it, you figured it out? Okay, anybody else? Anybody want to volunteer what they think it is? 3, why 3?
Then perfect weekend.
Right, so what are the pigeons again?
Socks.
Socks,
Boxes are your feet.
and the boxes are the colors, right? Yeah, or you could say your feet too, either way. So yeah, I've got a blue box and a black box, right? And I put all the blue socks in the blue box and the black socks in the black box. Well, if I grabbed 3, guaranteed that 2 of them have to be the same color. All 3 might be black, but guaranteed that 2 of them would have to be the same color. Does everybody see that? Does that make sense? That's a pigeonhole problem. And I remember when I first heard that as a kid, that the answer I gave was 5 as well. That's a very common answer that people would go to, is 5. And when somebody explained it to me, it made sense. But again, as a child, I'd never heard the pigeonhole principle. I didn't know what that was, but anyway. Fascinating. So why do we care about all this stuff? Who cares about counting and this? And we haven't even gotten to permutations, combinations yet. That's on Wednesday, it's also counting, and it ties into this stuff about does order matter and does it not matter? And in one case, you're dealing with the permutation, in other case, you're dealing with the combination. And we'll look at that in a little bit, and how do we subtract out the duplicates because order does matter, or because order doesn't matter, and so forth. How do we subtract all that stuff out? I said that funny, but I think you get the idea, right? So why do we care about this stuff? We've looked at some problems today that I think are somewhat relevant. I mean, the number of socks is not a relevant problem, right? But there are some problems we kind of looked at today. Maybe the number of passwords, the number of possible phone numbers, that if we're in charge of that kind of thing. There's also some examples in the book about the number of IP addresses that are possible. Now think about when the IP address was first a thing. I mean, there wasn't a world where, how many computers, any one of you, who thinks they have the most number of computers out of the people in this room in their house? And that includes your phones, everything. What's the most somebody owns? I have, like, actually operating, I have some dead phones I don't use anymore, but actually operating in our house, there are 2 smartphones, 4 tablets, we have a Mac desktop, a Mac laptop, I got a Linux box laptop, I got a PC desktop, I got this laptop here, I've got a Surface Pro. I don't know how many is that, it's like 12 or, I don't even know, I stopped counting.
Projectors have IP addresses, right?
Some may, newer ones might, but older ones probably not. But not IP addresses, but, did I say IP? I meant MAC addresses, sorry. I said IP, but I meant MAC addresses, sorry about that. But there's a lot, right? My house has 1 IP address, right? Okay, now you can set things up to have multiple. In fact, the whole thing with subnet masking, which we don't get into in this class, that was to deal with this problem of everybody having multiple computers. So you have a company that has 10,000 computers in it. Well, they may have only 1 or 2 IP addresses, and then you do subnet masking to deal with the internal ones. But MAC addresses, how many possible MAC addresses are there? You guys know what a MAC address? Media Access Center. That's a number that's unique to every single piece of hardware on the planet. So everybody's NIC card or network card has its own MAC address. In fact, my router is set up at home to, if I don't have your MAC address in my router, you can't get on my Wi-Fi, right? It's for security reasons. So when my friends come over, like, what's your Wi-Fi password? I'm like, it doesn't matter if I give it to you because you can't get on, right? Because you have to, I'm not gonna put your MAC address in. Because I gotta log into my modem and, anyway, but the point is, no, I'm nasty. The point that I'm getting at though is, we're in a place now where we're running out of IP addresses, even when we're dealing with subnet masking. The IP4 is the current version, which by now I think they've probably started switching over. Is it IP7? Is that the new? IP6? Yeah, 6, yeah. It's a different thing, but these kinds of questions come up. This is a discrete counting problem. How many possible IP addresses can I have? Is that enough? Is trillions enough? Well, when you think that there's only, how many people on the planet? 7 billion? You think 7 billion and like having, 21 or 30 billion IP addresses is probably enough, but maybe it's not, right? We're living in this world where everything's got an IP address or a MAC address or whatever, right? So this is one of the reasons we care, right? This stuff is important, and we looked at some simple problems that are small versions of these bigger problems, right? But let me ask you a question here. This seems like a simple question, and you're going to know the answer, no problem. What is the probability that I'll roll a 1 on a normal unweighted 6-sided die? I got a regular old die, and I roll it. What's the chance I'm going to roll a 1? 1 out of 6, which is the percentage of that is 16.7%, right? So we intuitively know that that's 1 divided by 6, okay? In other words, that's number of favorable outcomes divided by possible outcomes, right? Number of favorable outcomes is just 1. I wanted to roll a 1. If I ask the question, what's the chances that I'd roll an even number? Well, then it becomes 3 over 6, right? 2, 4, and 6 divided by 6 total outcomes. It's pretty simple, right? That's probability. Probability is no more complex than that. It's some number divided by some other number. That's it, right? The question is, though, what is the favorable outcome? What are the possible outcomes? Those two numbers, the numerator and denominator, can be hard to find. Okay, so discrete probability is about favorable outcomes divided by possible outcomes. With a dice, it's easy. With dice, it's easy. But sometimes knowing what the numerator and denominator that's tricky stuff, okay? So for example, what's the probability of getting a full house in a game of 5-card poker? Now, you may know if you're a card person or a gambler or whatever, you might know these numbers, right? You think I'd know being a card magician, but I don't. I have a little cheat sheet that tells me what they are. But how do we figure that out? Well, it's favorable outcomes divided by possible outcomes, right? Favorable outcomes over possible outcomes. Well, what are the favorable outcomes? It's
Two are favorable?
well, it's the answer, I don't want the number, right? It's the favorable outcomes, it's a full house,
Okay.
okay? What are the possible number of 5-card hands that can exist? That's the possible outcomes. Okay, we're gonna learn how to calculate this later. We're not gonna solve this today. That's a big number, right? We have to use combinatorics to figure these out.
Mine is 52 times 51 times 50 times,
Not quite.
not quite?
No, that's how many possible ways you can shuffle a deck. 52 factorial. That's how many ways cards can be shuffled. But I'm looking at a deck of 52 cards, and I need to pull out 5 of them. So how many ways can I do that? Right? Yeah, I heard, did you say it? I heard to choose, 52, choose 5, right? Yeah, we'll learn about that when we get into combinatorics and stuff on Wednesday. But again, the point is, how do I know what is the favorable outcome? How do I know how many full houses are possible? How do I figure that out? Right? How do I know how many 4 of a kinds are possible? How do I know how many royal flushes are possible? That's easy. How many? 4, right? There's spades, hearts, clubs, and diamonds, right? It's always ace through 10. There's only 4 of those. That's easy to count. But how many full houses are there? Well, there's 2 aces and 3 2s. And then there's 2 2s and 3 aces. And the 2 aces might be the spades and diamonds, or they might be the spades and the clubs, or it might be the hearts and the diamonds, it might be, right? There's so many different ways to do that. How many possible ways can I get a full house? We have to figure out that. Then, how many possible ways can I just get 5 cards at all? Then I divide that first number by the second number. That's the probability of getting a full house. We will solve that problem on Wednesday, okay? Not today. But this is one of the reasons why we care. Well, why do I care about the playing the poker hands? I don't. But they're easy and fun problems to work through for stuff that really does matter. We're going to work through pretty much every possible winning hand or any possible hand on Wednesday because it's good practice to understand how to do this kind of probability and how to use permutations, combinations, and all the stuff we learned today. But why does that matter? Why do we care about probability? There's a little summary of what I just said right there, right? Okay? Solving this stuff requires the techniques we learned today. The reason this matters is discrete probability is the foundation of Bayes' theorem and Bayesian statistics. Okay? And that's basically the last day of class we get into Bayes' theorem. The last day or two we get into Bayes' theorem and Bayesian statistics and what that's all about. But that's used in the real world everywhere, right? Spam filters are based on Bayes' theorem. The basic idea of Bayes' theorem is given that this event has occurred, what's the probability that this other event will occur, right? And so the spam filter, what's going on there, and we'll look at the formula for it later, but the spam filter, the basic idea is, well, given that this email that I'm looking at, this filter is looking at, that it has these keywords in it, what's the probability that it's actually spam, right? How do you figure that out? Well, that's what a spam filter does, and you can dial it up or down, and you're using Bayes' theorem. Bayes' theorem is all about probability. Probability comes down to something divided by something. Well, figuring out what the something is that's being divided by the something else can be tricky business. Permutations, combinations, counting, all the stuff we looked at today, pigeonholes, all this stuff plays into that. And again, I mentioned this, it's in spam filters. This is also used for when we're going to look at a problem. I don't want to say too much because we're going to look at a problem on Wednesday that deals with this. But it's when taking medical exam, like what do you call them? Not medical tests, but screening. Like you're going to get a cancer test or something like that, see if you have cancer or AIDS or something like that. The Bayes' theorem is involved in that, believe it or not. Sorry, I couldn't think of the right phrase, and I'm not even sure if screening is the word I was looking for, but it works, right? So, but you get the idea. These kinds of things are, if my blood work shows that I have cancer, what's the probability that I really do have cancer? That's a question that's important to know, right? So we look at those when we get into permutations, combinations, and we get into Bayes' theorem and all this stuff. It's all there. And we'll use trees to figure out some of the stuff, and we'll use some of the counting techniques and so forth. And again, to understand Bayes' theorem, we have to understand probability, okay? And if you're gonna understand that, you have to be able to calculate on doing all these counting techniques. I think today all the counting we did is pretty easy. I think you guys are pretty comfortable with it. It's not that hard. It gets trickier as we go along, I promise. When we look at stuff on Wednesday, you'll see how much trickier it can be. The probability of this being the last slide is about 99.99%. Yes.